Just for the record, what I'm trying to do, I'm trying to expand my Canvas skills, which there is plenty of room for improvement on that. So what I'm going to try to do on this module, Module 2, which is for this week, is once I post this video, then I'm going to try to make it where you have to at least open up that video before you can go through the rest of the module. So you guys are obviously seeing it in person, so you don't need to watch it in its entirety, but you're going to have to at least click on it and open it up, and then you can get out of it and go on. But it won't let you go on to like Wednesday until you at least open up that link right there. And this is going to hopefully give me a better way of monitoring how people that are virtual are doing. Are they really doing what I want them to and stay caught up, and especially the kids that are online, so I can tell if they're actually watching the videos or not. So that's my intent. But questions on the homework? Anything from homework 5 or that you would like to see?
Can you do 15?
Do you know what that one is? I need to break out my book. So this is on the logarithm stuff, is that right?
Yeah.
So it's, I think, 7 to the x plus 2 equals e to the 17x?
Yeah.
Okay, yeah, that's a tough one. So 7 to the x plus 2 equals, because what we have here is two exponentials that are different bases, and that's particularly difficult. It's e to the 17x. So I think the preferred way of doing it, because at some point in time we're going to have to get on a graphing calculator anyway. So I think the most efficient way is to either call this side y1 and this side y2, graph them on your calculator, and then try to find where they're going to intersect.
Okay.
And the problem sometimes there is you may have to play around with the window, the x min, x max, y min, y max particularly, to try to find out where they're going to cross. And sometimes that can burn through some time, especially if they get really big. So I think what I would suggest is instead subtract this one over so that you make it equal to 0. So you still may have to play around with the x min, x max window to figure out where it's going to cross the x-axis. But now you don't have to do this whole, how high up do I have to go? What's the y max going to be? So I can see the point of intersection, because you know it's going to cross the x-axis. You can set your y min and y max to -1 to +1, and you just look for where it crosses, and then use your find 0 option. Does that make sense?
Yeah, I was just trying to solve it algebraically. I didn't.
Well, and I think that let's do that too. So I'm going to let you do that, and I can't really show that very well on the video. So, but I'll also do it algebraically, which is tougher, and I don't know that would be the most efficient way. And this, I don't think you'd ever see something like this on an AP test, but I don't think it's particularly efficient, but it's kind of interesting. So let's come back and do it algebraically, because I think that's worth seeing. So the idea is here with the two bases, we're going to have to take the log of both sides. Now, since we have one of those is a base Euler's number, it's kind of nice to do a natural logarithm, because then at least we're only going to end up with one logarithm that survives. So you don't have to do it this way. You could do a common log, but I think this has at least a little bit of advantage of making it a little simpler. So on this side, these are inverses. So those are going to cancel, and you'll get the 17x. On the other side, we're going to bring the exponent out in front and get to there. Now is where it gets kind of crazy, because you just got to keep remembering natural log 7 is a number. So now this is really an algebra 1 problem, but with just crazy numbers. So I'm going to distribute that and call that x natural log 7 plus 2 natural log 7 equals 17x. So there's two terms that have x in them, and I'm going to bring them to the same side of the equal sign and leave the thing that doesn't have an x in it on the other side. So I'll leave the 2 natural log 7 there and subtract the x natural log 7 to this side. So now that we've gathered all of the x terms on one side of the equal sign, we can factor that x out. So that's going to be 2 natural log of 7. We'll factor that x out and get 17 minus natural log 7, which is a goofy number, but it's still just a number. So we'll divide that to the other side. And so now, again, we have something that's going to go onto our calculator. And so then you'll just enter that and come up with that decimal.
Okay.
Okay? Other questions from the homework? Okay, so we're going to talk today. I have to take a deep breath here because it took us, I don't know, 2.5 months to do this in AP Prep. We're going to review trig functions here in about 20 minutes. So, this will be a light review. We will, some of this stuff will come up regularly throughout the year. Others we will see quite a bit later, particularly stuff with the inverse trig function. So we'll revisit it as we need to, as we go through the class. So please, 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 if you don't remember how to do something with a trigonometry or anything else, ask. Okay, so you know, we don't want the pre-calculus and algebra stuff to get in the way of us understanding the calculus, which a lot of times does. You know, the downfall of most calculus students is the algebra part. So don't fall victim to that. So we will 100% of the time be in radians in AP Calculus. Always, always, always. So the big thing, and I'll remind you this when we get close to May 4th, but I will be telling you, put your calculator in radian mode and leave it there. Okay, so don't, I know in physics you go, people that have physics are going to be forever switching their calculus back and forth because they do everything in degrees, we do everything in radians, and so it's a potential disaster. Don't do that. So by definition, radian is the arc length, which I don't know why they call it S, but they call arc length is generally called S, divided by the radius R. So we say that theta, an angle given in radians, is S over R. Arc length divided by radius. So it's really nice in a unit circle. So in the case where you have a circle with radius 1, and that's kind of a nice way of thinking of it, then the angle becomes just the arc length. You know, so you can see since, you know, for example, circumference is 2 pi r, if the radius is 1, then one full circumference is 2 pi, and that is 2 pi radians, which makes a semicircle pi radians, and our 90-degree angle half of that semicircle, so pi over 2, and we're off to the races with those known values. Okay, so I'll come back to that in a minute, but we can answer a question like, say, the length of an arc intercepted by theta equals 2 pi over 3 radians in a circle with radius r equals 6 inches is what? So the idea is if our angle is in radians, then this arc length formula is pretty slick because we just multiply the r to the other side. So from here we get arc length is just theta in radians times the radius, which is pretty nice. So in our case here, since we have our angle, which is in radians, and we have our radius, then the arc length is going to be that angle in radians times the radius, if you're not philosophically opposed to canceling, we're going to get or pi, and what's the units on that?
Inches.
Inches. Nice, recovery, or just inches is what all the units are. You know,
At least you can do basic addition.
that's the part that's throwing you, okay? I don't know if I can help you with that. So if you remember just the relationship here. So, what's that? That's still recording. That goofed me up the first time. I think it's the connection to the TV or that part is shut down, like the laptop went to sleep, but the camera still working, so it's still recording. So yeah, first time I stopped everything and then I had my video in 2 pieces. That part I've learned. I have to make all the mistakes with technology before I can learn. So here's our angle theta. I'm just showing that there. And so the usual way we label things, we like to drop that perpendicular down to the x-axis. And so the coordinates of this point, the x and y coordinates of that point, we know that the x is this distance out to the point, which is that adjacent side of the angle, and the y is the vertical distance up to the point, and that is going to be the y coordinate of that point, or the opposite side of our triangle. And whatever the radius is of that circle is going to be the hypotenuse. So in really nice cases, the radius is 1, but it doesn't have to be, and we can still go from there. So we can then say, we know our relationship that, cosine of theta from SOHCAHTOA is going to be the adjacent over hypotenuse. And we know that sine of theta is going to be the opposite over the hypotenuse. And the tangent of theta is going to be the opposite over adjacent. So just reviewing and refreshing your memory on this. Then we have the reciprocal functions as well. So for cosine, we get secant of theta, which is the reciprocal of cosine. And since cosine is x over r, that's going to make the secant be r over x. I think most of us would figure out what the cosine is and then take the reciprocal kind of as 2 steps. The reciprocal of sine is cosecant of theta. So I'll write it as the reciprocal of sine, and that then will be r over y. The cotangent of theta goes by many different names. It's the reciprocal of tangent, and I guess we could also say tangent is also known as sine over the cosine. That's one of our definitions for tangent. And so if the cotangent is the reciprocal of tangent, that's going to make the cotangent be cosine over the sine. And in our scheme here, since tangent is y over x, that's going to make the cotangent be x over y. Okay, hopefully that's just brushing cobwebs off and not learning it for the first time. We talked about before, we made a huge deal of graphing in AP Prep, and I guess the good news is maybe that we're basically much less so in here. So we aren't going to do a lot of graphing of trig functions. I'll show you an example of what might be a more typical kind of question that we might have to answer. Not that we won't deal with trig functions, because we will a great deal, but not so much just for the point of the problem is to graph. It'll be what do you do with that graph once you have it. And to get the graph, a lot of times it'll either be given to you, printed on your test paper or worksheet, or you'll be able to use your graphing calculator as well. So remember, the A part is the vertical stretch, and we had this idea of what we call amplitude that we talked about with sine and cosine functions, and that it is the maximum value minus the minimum value divided by 2, and that is going to be that absolute value of A. So that coefficient of the sine or cosine curve is what does the vertical stretch. So we know that the basic fundamental sine or cosine curve goes from -1 to 1. So it's got an amplitude of 1, and then whatever multiplies that sine or cosine curve becomes the amplitude, the absolute value. The B is going to be the horizontal stretch or shrink. And remember, this goes kind of counterintuitive. So we know that with the A, a number bigger than 1 stretches it, and a number smaller than 1 shrinks it. But with B, because our period, the normal period for a sine or cosine is 2 pi, we divide that by the B to get the period, a new period after our stretch or shrink. And because you're dividing by that, that means that if B is bigger than 1, it's going to shorten the period, which is going to shrink the graph. So a number bigger than 1 shrinks it horizontally, whereas if that number is less than 1, when you divide by it, it's going to make it a bigger number. So that's going to be a horizontal stretch. So I talk about the nice way of remembering that is think of this as speeding it up or slowing it down. So if you have your normal sine curve, then if this number is bigger, then what it's going to do is speed it up and make it complete that full cycle faster, which ends up being a horizontal shrink. And the C is our translation or shift in the x direction. And the D is going to be then our translation or shift in the y. So the x, and remembering that a sine curve or a cosine curve is infinite, it goes forever. So, but it's going to slide everything right or left, depending on what that is, and the D is going to move it up or down. So a typical question is for us might be something like, instead of actually asking you to graph it, might ask you to find the period and range of, and then I'll give you y equal to 5 sine of 2x minus pi over 2 plus 2. Can you find the period? Because that's going to be an important idea still. And can you figure out what the range is? Where does that graph go from the low y value to the upper y value? What are those going to be?
The period is pi.
Nice, because the period is going to be the 2 pi divided by whatever is multiplying that x. So that part we got. How about the range? So without actually having to graph it, you're going to have to think about what actually happens. And I'm going to give you a visual, but you don't really have to do this. So where's the midline? Where's the middle of our graph going to be? 2. Yeah, that's our translation, right? Because a normal sine or cosine curve, the midline is the x-axis. And this is the vertical stretch or shrink. So it's going to get moved up 2. So the middle of our graph, the midline of our graph is going to be 2. And now what's the amplitude? What's the vertical stretch? That's the 5. And so from the midline of 2, we're going to go up 5 and down 5. Right? And so that's going to make the maximum value that the sine curve will ever equal is going to be 7. And the minimum value it'll ever be is -3. And so our curve, wherever else it goes, is going to bounce back and forth between there. And so that is going to make our range go from -3 to positive 7. So it's kind of a way of trying to think about it without actually making you take the time and effort to actually come up with the whole graph. So let me give you one, though, where I'm going to ask you to come up with the equation from the graph. So this will challenge us to remember how this works. Find an equation, because there'll be lots of different ones, an equation of, and give you the following graph. So we're going to say that at negative 5 pi, and at, do I want that to be? So some unknown number there, and then at negative 3 down here, and this is going to be pi, and so this will be pi. At any rate, this will be 13 pi, and then it's going to have a high of 5. So I'm going to do the right, and where the low is. We try it again. So let's do something like that. Okay, so it's going to go from negative 5 pi to 13 pi, and in dx, that's going to be one full cycle, and a minimum y value of negative 3 to a maximum y value of 8. Armed with that seemingly paltry information, and we come up with an equation of this curve. So should we decide, we can kind of do it together here. So what, do you want to think of it as a sine curve or a cosine curve? Because we could do either.
Negative.
You want to think of it as a negative cosine. Okay, so
What?
you got to speak early if you want to choose something different, because Miranda's taking over.
No, that'll take over.
That's okay. So where is your negative cosine curve then going to start? What's your starting point? If it's a negative,
Negative 5.
yeah, it's going to start right here, right?
Wait, what?
So a negative cosine has to start at a low point.
Wait, then I want sine.
I think that's a good choice. I think sine curve,
I got confused.
that's okay. And you still want to make it negative?
Yeah.
I think that's a good choice as well. I think Tim's feeling better already, except when he has to erase what he already put down.
Oh my gosh, 3 hours.
Okay, so it's going to be a sine curve. So where is this thing going to start?
At negative 5.
Yeah, at negative 5 pi. So whatever, we don't know what the b is yet, but that's going to be an x plus 5 pi. Is that okay? So how about our amplitude? What's the a, the number in front of that sign, going to be? We decided it's going to be a negative.
4.
Yeah.
So it's max minus min divided by 2. So that a that we're going to plug in here is going to be the 5 minus negative 3, which is 8 divided by 2. And so that's going to be a 4. And negative because it's a negative sine curve because we're doing that loop below part first. Okay, how about the translation vertically? What's the midline of this thing going to be?
1.
It's going to be 1, right? So 8 is from top to bottom, half of that is 4. So either counting up 4 from the negative 3 or down 4 from the 5 is going to make that be a 1. So you have a plus 1. Now the hard part is always figuring out the b. So remember we said that 2 pi divided by b would be the actual period. So that means that 2 pi is going to be b times the period. That means b is going to be 2 pi divided by the actual period. So our b, that number that we're going to plug right here, that b is going to be 2 pi divided by, what is that period? 18 pi. So that's going to be just 1 night. Okay, there we have it. Okay, so let's talk a little bit about inverse trig functions. And again, we will do more with this as we need it down the road. But if you remember, our sine curve does something like this, but it goes on and on and on forever. So it has a maximum y value of 1, minimum of -1, and it's going to have intercepts at multiples of pi. So we said before, this is a good chance for us to remember, we said what must be true about a function if it's going to have an inverse that is a function?
It has to pass the horizontal.
Ah, very good. Okay, so I'm going to say be invertible. One way of saying that is it has to pass the horizontal line test, which this clearly does not. What else did we say? Another way of saying this, horizontal line test. The horizontal line is going to intersect this in an infinite number of places. What else do we say? What's another name for a function that does have an inverse that is a function, that does pass the horizontal line test? It could be called
1-to-1.
Oh, 1-to-1. It is a 1-to-1 function. Thank goodness you're in here, Tim. You're getting no help from anybody else. We learned a new way of saying if a function is 1-to-1, it must also be always increasing or always decreasing, which we learned a new name for not long ago. Who could forget? No, don't answer that. What is it called? Strictly monotonic. Nice. Okay, anyway, this is not any of those things. So what we do is we restrict the domain. And so what we do for a sine curve is we restrict the domain from -pi/2 to +pi/2. Okay, so if we choose our domain to go from -pi/2 to pi/2, then y equals sine x is a 1-to-1 function. It is strictly monotonic. It does pass the horizontal line test. Therefore, it does have an inverse function. And its range, I should say, on this interval still goes from -1 to 1. Okay, so that means it does have an inverse. And so we could say the inverse function is written to suggest that idea that it is an inverse function. You see this notation sine inverse. That's not a reciprocal of sine. That's not a cosecant. It is also written, remember, as an arcsine. So arcsine and this notation, inverse sine, are synonyms. They mean exactly the same thing. Okay, and its domain range then, because it's an inverse function, we're going to swap what it was for the sine curve. So its domain, you can plug in numbers from -1 to 1, and you will get out, this is, I hope we have time for this, you're going to get out from that answers that are between -pi/2 and +pi/2. Okay? I don't think we're going to make it, guys. In a similar fashion, we have a cosine curve, and we have an inverse cosine, or also known as an arc cosine of x. So in a cosine curve, we restrict our domain to be from 0 to pi. So we just look at that piece of the function. And with a tangent curve, which remember, it's got these asymptotes at pi/2 and -pi/2. So we just look at that cycle right in there. And so this is the part that we look at for a tangent curve. And then we will have an inverse tangent or an arc tangent as well. So I want to talk briefly in 2 minutes, I guess, or less, about we need to know these important values of sine and cosine. So I have here, I'm going to give you a blank copy of, it's actually two-sided, of what will become known as the chart quiz, because we're going to have a quiz on this. Not to totally scare you, but when we take this quiz, which is somewhere on your module, it's going to be next week sometime, you will have to complete that entire thing in 5 minutes or less to perfection. So you have to get all of it right in 5 minutes or less. So to recall and remember, I'm going to look at, say, y equals the sine of x. We need to know the values at 0. So that's going to be pi over 4. That's going to be pi over 6. That's going to be pi over 3, pi over 2, and then all the way around the circle. So if you remember the sine of 0, so sine is the y-coordinates, which starts low and gets bigger as we move from 0 to pi over 2. So the values of sine, which are the y-coordinates, are going to be 0, and then at pi over 6, it's going to be a half, and then we'll get square root of 2 over 2 at pi over 4, and square root of 3 over 2 at pi over 3. Finally, as big as it gets, 1 at pi over 2. We can talk more. What I'd like you to do is see, in a calm, relaxed way, see if you can fill out that one side of that chart quiz. The answers are online, are on the Canvas, so they're posted there so you can check them and then do the homework as well. So, and then we'll talk more about what we're going to do in terms of the quiz, but I want you to practice those and know them so well that you can just move down there and fill that whole thing out in 5 minutes or less.
What does the second column mean?
Second column is that's degrees, that's in radians. So I think it's telling you, so that's just the angle in radians.
So,
I'm sorry, given a range, you want to do.
okay.
So it'll be like pi over 4 is 45 degrees.
Will there be a second sheet on it? Or
So the first one you can fill out and you can check it on there. Yeah, there's a blank one if you want to print out more for practice purposes.
Okay.
And I'd practice a few of them,
Yeah.
and then after you've done it a few times, then put yourself on the clock and make sure you can do it in under 5 minutes.
How long did it take to master it, Austin?
Nothing?
Yeah.
Probably about 2 tries.
Well, some people take a little longer. Austin,
He's a stud.
And then 6 and 7 for Thursday.
what's that? Yes. We're going to have your Chromebook with you. We're gonna do the also see.
How is it? I have 3 classes in the morning, but my backpack is still heavier when I have stat.
It's not the quantity, it's the